All right, so let's go ahead and do that more complicated example I was referring to previously. With this example, we're going to compute the Laplace transformation of sine of AT and see what we obtain. So for convenience, and you're going to see why this becomes useful later on, let the following be equal to f of s. This was referring back to that notation we saw previously. And recall what this equals. This was the integral, and this is just the definition of Laplace transformations of e to the minus st times sine of a times t, okay, with respect to t. And this is going to be equal to the limit as n goes to infinity. The integral will be from 0 to n. This will be e to the minus s times t times sine of at dt. Okay? So by integrating by parts for this expression, based off the input that we saw previously, as you'll notice, this was f of t, and that's what gets plugged in here. We can integrate this expression by parts, in this case, letting v be equal to sine of a and t, and u being equal to e to the minus st. As you remember, integration by parts says uv minus the integral of v du, right? So if I was to let dv be equal to the sine of at, what does this equal? Right? And that's the question we're about to answer here. Well, that will be 1 over a times the cosine of at. But specifically, that's exactly right. Oh, sorry, one last thing. It should be a minus sign. Why is that? Because if you were to take the derivative of this, what would you get back? The derivative of this, a cosine, would be negative sine, right? Negative sine times a, and that would give us back the positive sine of at. So that's what you have here. And then u is going to be equal to e to the minus st. So therefore du, with respect to t, it's going to be minus s times e to the minus st. Okay? So with all that known, we can then proceed to answer this question, what does an integration by parts look like for this? Okay? So let's go ahead and just plug all these values in, and we should obtain the following answer. What we obtain is f of s, okay, is going to equal the limit of n goes to infinity, okay, and this will be minus 1 over a, okay, e the minus s times t, okay, times the cosine of at, close parentheses, and this goes from 0 to n, all right? The limit's not done yet. We still have some items within this, so it'll be minus s over a integral 0 to n e to the minus s times t, okay, times the cosine of a times t dt, and then we're done, okay? So you'll probably notice that although this expression up above is not too hard to work with, and I mean this expression, This one is still an issue. So we have to integrate by parts again, and therefore integrate by parts twice. So like before, you remember where we had dv equal to sine at, now we have dv equal to cosine at, and then we rinse and repeat integration by parts again. So I'll leave it to you to check my work, but this is what you should obtain if you do it correctly twice, another time with integration by parts. You should get the following answer. It'll be the limit as n goes to infinity, okay? It'll be 1 over a, all right, times 1 minus e to the minus s times n times the cosine of an, close, and close, okay? Still not done with the limit, minus s over a, and this is the second integration by part results, 1 over a, e to the minus s times n, and this time it's sine of an, and I should tell you these expressions here are going to be very important here pretty soon, plus s over a times the integral from 0 to n, e to the minus s times t sine of at dt, close, close. Okay? That's what you should obtain. And afterwards, you can simplify. And if you simplify correctly, you should see that capital F of S is equal to 1 over A minus S over A, okay, times S over A times the improper integral 0 to infinity, e to the minus s times t times the sine of at dt. And that's going to close parentheses here. Okay? You can simplify this again, and you get 1 over a minus s squared over a squared, okay, times the improper integral from 0 to infinity, e to the minus s times t sine, all right, at dt, just like that. And so in the next video, I'll explain how we can take this one step further and simplify this one more step.